Hi, I'm Mark Barsamian. In this video, I'll be discussing derivatives of logarithmic functions. The reading for this video is section 3.2, derivatives of exponential and logarithmic functions, more specifically from the bottom of page 188 to the middle of page 192, examples 2 and 3. The corresponding homework is this collection of 6 problems from section 3.2. We'll be using some prerequisite skills, these properties of logarithms. The logarithm of a times b is not ln of a times ln of b, it's ln of a plus ln of b. The logarithm of a to the b power is b ln of a. The logarithm of 1 over a is minus logarithm of a. And finally, logarithm of a quotient, a over b, is ln of a minus ln of b. It's worth recalling the shape of the graph of y equals ln of x and why it has that shape. Remember that the graph of y equals ln of x is obtained from the graph of y equals e to the x by interchanging all the x, y values. So let's label the distinctive points on the graph of y equals e to the x. There are those 3 distinctive points. We interchange the x, y values of those points and we get these new points. Those are points on the graph of y equals ln of x. Now, these points tell us some useful values of ln of x at particular values of x. Let's go back and recall where these points on the graph of y equals e to the x came from. Those 3 distinctive points came from these 3 straightforward calculations. Well, most students can remember these things or make sense of them, but students don't usually remember the corresponding easy calculations involving ln of x. So for that, it's helpful to think about these distinctive points that came from these distinctive points. Now think about what these distinctive points tell us about the behavior of ln of x. So while most students can remember these things, very few students can remember these things. And you realize that they come from the same place. Now let's think about the shapes of other logarithm graphs. We have the general log base b function obtained from the graph of y equals b to the x by interchanging the x, y values in the same way that we just did on that graph of y equals e to the x and y equals ln of x. Let's label these 3 exponential functions. We've seen these graphs before. And let's label the distinctive points on those graphs. So there are the distinctive points on those 3 exponential function graphs. When we interchange the x, y coordinates of all those points, we get distinctive points on the graphs of the corresponding logarithm functions. That's this collection of graphs down here. Let's title those. So there's the collection of distinctive points. Now, they tell us about convenient calculations involving the logarithm. Just as we have those convenient calculations involving exponential functions. Now, remember that we had a collection of common properties of the exponential function graphs, properties of the domain and range, distinctive points, the end behavior, and the graphs increasing from left to right. Well, we'll have a similar collection of common properties for the logarithm functions. Let's think about the domain. The domain of the logarithm graphs, the set of x values for which you have y values, is this set the set of all x's that are greater than 0. The range, the set of y values that you can get as a result, is that set, the set of all real numbers. Okay, what about the end behavior? Well, notice that the left end of the logarithm graph is actually here, right in the middle of the page. The graph has a vertical asymptote with line equation x equals 0, and the graph goes down along the right side of that asymptote. The other end of the graph, the right end of the graph, is over here. The right end of the graph goes up without bound. Also notice that all these logarithm graphs are increasing. As you go from left to right, the y values go up. So there's our collection of properties all put in one table. The domain and range. The domain is a set of all positive x values, so denoted that way. The range is the set of all real numbers y, denoted that way. There's that collection of distinctive points and what they tell us about how the log function behaves. Here's the description of the end behavior. The graph goes up without bound on the right, so that limit expression tells us that, describes that. The limit as x goes to infinity of log base b of x is infinity. The graph goes up on the right. On the other hand, the graph has a vertical asymptote with line equation x equals 0, and the graph goes down along the right side of that asymptote. Well, in a limit expression, that would show up this way. That x equals 0 shows up here, x approaching 0. The fact that we're approaching from the right side of the asymptote explains why there's a plus sign there. And the fact that the graph goes down along the right side of that asymptote shows up here as that negative infinity symbol. And then finally you see that the graph is increasing from left to right. That's included in our list of properties. Well, let's learn some derivative rules. The first new derivative rule we'll learn is this logarithmic function rule number 1. It's used for finding the derivative of the natural logarithm function. That is this one. When f of x is ln of x, it turns out that f prime of x is 1 over x. You can express that as a single equation. D over dx of ln of x is 1 over x. Now here I should make something very clear. You have to be careful how you read that equation. Notice the d over dx goes with the ln of x. It does not go with the 1 over x. On the left side of this equation, we have d over dx of ln of x. On the right side of the equation, we have 1 over x. We do not have the d over dx symbol here on the right side. It's very common for students to misread this symbol. They see this. They see that equation, they think that it's telling us that ln of x is 1 over x. That's not true. ln of x is not the same thing as 1 over x. So many times I've seen in students' papers this written, that ln of x equals 1 over x. Students get confused about this. It's just simply not true. ln of x is not 1 over x. The relationship is the derivative of ln of x is 1 over x. All right, so where does this rule come from? Well, it's found by using the definition of the derivative. So in other words, you would set up one of these definition of the derivative calculations where you compute f prime by doing this crazy limit. So when you use the logarithm function, that limit would look like this. Limit of ln of x plus h minus ln of x over h. And you would compute that limit. In the book they have the calculation shown on page 189 to 90, and they use the four-step process, and it's very interesting to read. You won't be called upon to do that calculation in Math 1350, so I won't discuss the details here. But it is worth discussing why that rule makes sense. So we'll gain a much better understanding of that rule if we examine the graphs of f of x and f prime of x. So remember what the rule says. The rule says if f of x is ln of x, then f prime of x is 1 over x. So what I've got on the next page are computer-drawn graphs of y equals ln of x and y equals 1 over x. So this top graph we have f of x. And on the bottom we have f prime of x, which is 1 over x. Notice that these are not the same graph. Ln of x is not the same as 1 over x. All right, now remember what we're supposed to do. We're supposed to compare the numbers that are the slopes on the graph of f of x to the numbers that are the y values on the graph of f prime of x. Well, we can actually label these points very clearly using what we know about these functions. So on this graph of y equals ln of x, I've got those three distinctive points shown. So let's put coordinates on those points. And at those same x values, I've shown points on the graph of 1 over x. So let's put coordinates on those points. Now we know the x coordinates. They're the same as the x coordinates on the graph above. So let's start by putting those x coordinates in. Now how do we get the y coordinates? Well, we have a function here with a formula y equals 1 over x. So that tells us that to compute these y values, we just simply use this formula. I'm going to do that, and I'm going to write the y values in red. So 1 over e is e. 1 over 1 is 1. 1 over e is 1 over e. So those are the y values on the graph of 1 over x. Well, remember the relationship. This graph is the graph of the derivative of that function. So that means that these y values must be the numbers that are the slopes on this graph. So we should draw the tangent lines on the graph up here and label them with their slopes. Well, see, we actually know the slopes. These numbers that are the y values down here are the numbers that are the slopes of those tangent lines. So the numbers that are the slopes on the graph of f of x equals ln of x are equal to the numbers that are the y values on the graph of f prime of x. Now notice that these abstract numbers actually make sense. So in particular, the number e is a number that's close to 3. So the y value of this point is very close to 3. And the x coordinate of this point is very close to 3. So and the y coordinate of this point is very close to 1/3. In terms of the slopes on this graph, notice this tangent line is much steeper than this tangent line. The slope of this tangent line is close to 3. The slope of this tangent line is just the number 1. And the slope of this tangent line is close to 1/3. So it's not as steep. So the relative sizes of these y values and the relative sizes of these slopes make sense. So to reiterate, in terms of a graph, it is believable that the derivative of ln of x is 1 over x. All right, there's another derivative rule. Logarithm function rule number 2. This is used for finding the derivative of a base b logarithm function. It says that if your function is log base b of x, then the derivative is 1 over x ln of b. Expressed in a single line, it says this: d dx of log base b of x is equal to 1 over x ln of b. Now, log function rule number 1 is actually just a special case of log function rule number 2. What do I mean by that? Let's go back up and look at log function rule number 1. log function rule number 1 has a left side that is d dx of ln of x, has a right side that's 1 over x. Well, let's see if we can get this rule by using log function rule number 2. So there we go. We have a calculation that has on its left side d dx of ln of x, and on its right side 1 over x. And in the middle, we used logarithm function rule number 2. So that's what I mean by saying that log function rule number 1 is just a special case of log function rule number 2. And notice that here we've used that distinctive convenient example of a xy pair on the graph of ln of x. ln of e is the number 1. Remember where that came from. So remember on the graph of ln of x, we found this calculation, ln of e equals 1. That came from this distinctive point, the point e comma 1, which came from this distinctive point on the graph of y equals e to the x, 1 comma e, and that came from this easy calculation that e to the 1 equals e. Let's do some examples. Example A. Find the derivative of f of x equals 12 ln of x. So you see that our derivative, even though we know these new rules, our derivative calculation begins with a simple rule, one of our old rules. We have a constant multiple, that's the number 12, so it slips right through the derivative symbol. The next thing we use is our log function rule. That says that we can replace this expression, d dx of ln of x, with this expression, 1 over x. And again, I want to stress, ln of x is not equal to 1 over x. It's d dx of ln of x that's equal to 1 over x. Do another example. So this calculation, again, started with the constant multiple rule, and then we used log function rule number 2, told us that d dx of log base 13 of x equals this stuff, 1 over x ln of 13. That's this rule. d dx of log base 13 of x equals 1 over x ln of 13. For question C, we have to use the fact that in our math book and in a lot of math books, this symbol, log parentheses x, actually means log base 10 of x. Now, I'll give you a warning here. In some books and in some computer programs, this same symbol means ln of x. But in our course, it means log base 10 of x. So let's do the calculation that way. So this question C would unfold just like question B. Question B, we found the derivative of 12 log base 13 of x. We did that, and we ended up with that. In question C, we take the derivative of 12 log base 10 of x. We're going to end up with the same thing, but everywhere there was a 13 in this earlier calculation, there's going to be a 10 in this later calculation. Finally, question D. Now here you're supposed to not fall for the common trap. notice that when you took the derivative of 12 ln of x, the result was 12 over x. You might look at this and see, oh, we're taking the derivative of 12 ln of 13, so maybe we'll just get the answer that the derivative is 12 over 13. Instead of 12 over x, we might have 12 over 13 down here. But that's not correct. The key is to notice that this function has no variable in it. It's a constant function. So its derivative is the number 0. We don't use the constant multiple rule because we don't have a constant multiple. We have a constant function. Let's go on. Question E, find the derivative of 12 ln of 13x. Well, how do we do this? Let's go back up and look at our rules. Log function rule number 1 is this. d dx of ln of x is 1 over x. Log function rule number 2 is this. d dx of log base b of x is 1 over x ln of b. Both of those rules have just an x inside the parentheses. Just an x inside the parentheses. Neither one of our rules will work on a function where there's something else inside the parentheses. So what we have to do is we have to rewrite the function in a form where our rules will work. We have to rewrite the function in a way that there is nothing else inside the parentheses. So we have to rewrite f of x into a form that will work with our derivative rules. That is, a form where there is nothing inside the parentheses but just x. Here I've used that property of logarithms from the very first page. ln of 13x is ln of 13 plus ln of x. So there we have our function rewritten in a way that the only thing inside of the parentheses is the x, or the number 13. So now we're ready to find the derivative. Well, notice that we recognize these results. We've done these before. This derivative we did in question D. We got the number 0. In this derivative we did in question A. We got the result 12 over x. So the end result is 12 over x. Question F. Find the derivative of this function. F of x equals 12 ln of 13 over x. Well, we have to do what we did in question E. We have to start by rewriting f of x. So we rewrote our function using one of our earlier properties of logarithms. Log of a quotient is the difference of the logs. Now we're ready. We have a function that does not have anything else inside the logarithm besides just an x or a number. So we're ready to find the derivative. And again, we spot our earlier results. And our result is minus 12 over x. We have two more short examples. Question G, find the derivative of this function. F of x is 12 ln of x to the 13. Well, again, notice that the thing inside the logarithm is not just x, so we have to rewrite the function. So we use the property that ln of a to the b is b ln of a. Now we're ready to find the derivative. So the result is that f prime of x is 156 over x. We used the constant multiple rule. We had two constant multiples. Well, basically one constant. 12 times 13 is one number. And then we used our logarithm rule number 1. The derivative of ln of x is 1 over x. And again, ln of x is not equal to 1 over x. It's the derivative of ln of x that's equal to 1 over x. Our last example for this video is to find the derivative of this function, f of x equals 12x ln of 13. Now you might think that we need to rewrite this, but we don't. Watch. So our result is that f prime of x is 12 ln of 13. Notice that we used the constant multiple rule just once. We had a constant multiple in front of the x and after the x. Those both slip right past the derivative symbol, and they end up sitting in front side by side as one great big constant multiple, 12 ln of 13. The x gets snagged. That's the only thing in that whole expression that involves x. And it gets snagged, and we end up having to take its derivative. We take its derivative with the power rule. It's not an ln function. It's not an exponential function. It's just a power function. That's the end of that example, and that's the end of the video. Thank you.